So, you have seen how Lorentz transformation works, and when we go from one frame to other frame, things change, and space and time, x, y, z coordinates represents space and time represents time coordinate. As long as we are in one frame, we can talk separately x, y, z as one part and t as other part, but when we change frame, and once again in that frame we can talk separately space and time, but there x, y, z coordinates, if I am writing in terms of the x, y, z and time here, they all gets mixed up, and so we say that it is one entity, that is space time, and space and time, they act as components, and when you change frame, the components change, but the space time remains the same. So, we described 4 vector concept, where there are 4 components. One is time component c into t naught, and then you have x, y, z. So, these 4 components make a 4 vector, and they transform to another frame through some transformation equations, which are quite similar to the transformation equations when we rotate the frame in our usual 3-dimensional geometry and then construct a transformation matrix and see how that in the rotated frame what are the coordinates and how they are related to the initial coordinates. So, those things we have done. Now, let me move to dynamics, and dynamics means this is the force and this is the acceleration and this is the motion and this is the linear momentum, this is the kinetic energy. So, all those things which involve mass and forces that makes it dynamics, right. In kinematics, so far velocity addition or length contraction, we did not talk of mass, we did not talk of force acting on it and then motion being generated. So, those things we will be now doing, which is relativistic dynamics. Now, the dynamics is controlled by Newton's laws of motion in our daily life. We know that the force is mass times acceleration, and from there we do all kinds of conservation laws and this and that, and then we describe varieties of motion in this world. But Newton's laws are not invariant under Lorentz transformation, and if Lorentz transformations are describing the nature, then Newton's law cannot describe nature, because they are not invariant under Lorentz transformation, and principle of relativity, if you honor that, then these are inconsistent. So, when we go to high speeds, we do see deviations from Newton's laws, and therefore, yes, Newton's laws are to be modified. Only in low velocity limit, when Lorentz transformation also reduces to Galilean transformation, Newton's law become valid to describe motions. Most of our motion that we encounter are in this region, low velocity region. Low velocity means compared to 3 into 10 power 8 meter per second, the velocities are low. So, most of the world that we see or we experience, that contains only the low velocities, and therefore, Newton's laws are very good. We use it with all respect and everything. We make use of Newton's law, we derive our solutions, and they work out very well to describe everything that we see. But in laboratories, where I can accelerate an electron or an ion or a proton to high speeds, there Newton's laws are to be modified. So, that is the thing that we will be doing. So, first, from Newton's law or otherwise, we know there is a principle called conservation of linear momentum, extremely important principle. So, if I look at that, linear momentum P we write, it is related to force also. So, if you have a single particle and then there is a force on it, this force is related to rate of change of this linear momentum dp dt. In Newtonian mechanics, we define P as mass times velocity, and mass is a constant quantity. It is a characteristic property of that particle itself, and therefore, when you put it here, this becomes m dv dt, and that is m times a, F is equal to m a. And if you have a system of particles, a collection of particles, and there are forces on these particles from each other and from outside, then you have this equation still valid, but then this F is the total forces all taken together, and you call it F external, that is equal to dp dt. That is still valid. The internal forces, they occur in pairs and therefore they cancel out, and hence if this is 0, if external force is 0, dp dt is 0, and therefore P is constant. This is known as principle of conservation of linear momentum. So, first I will take an example and see if this principle of conservation of linear momentum with this definition P is equal to m times v is valid when your speeds are high, or it has to be looked into. So, I take an example, a specific example. Let us take two particles A and B on the x axis, each of mass m naught, and then they are moving towards each other with same speed u. So, this is the starting situation. You have two particles, they have same masses m naught, and they have same speeds u and u, and then they are going towards each other. The collision is not head on, and there is some slight shift, and hence after collision these particles pick up a small velocity in y direction also. Okay. This is they make collision, and our collision will be elastic. So, let us take this elastic collision, and after collision this particle deflects little bit and this particle also deflects little bit. So, after collision this particle has gone here, suppose somewhere here is the collision, and then it has picked up a small speed in y direction, and this particle B, this particle A now is going this way, and this particle B which is coming, that also after collision picks up that small velocity and it goes this way. So, this is B particle. We will assume that we are taking a specific example only. So, we will assume that this collision is such that this y component of velocity is very small, infinitesimal of first order. So, here the component is ux and here the component is uy, and uy is quite small, let us write it delta u. Now, since it is elastic collision, the kinetic energy is same and situation is very symmetric. If you have to take kinetic energy same and linear momentum conservation we are always looking at. So, here the linear momentum is 0 in x direction, in y direction. So, here also linear momentum should be 0 in x direction and y direction, and therefore, these two should again be opposite each other, same line, these two should be on the same line, so that the linear momentum vector when added may give you 0, and the two magnitudes should be equal, and therefore, the speed here should be equal to speed here, and this component should be equal to this component, and this component should be equal to this component. So, this is ux and this is delta u, right. This is ux, this component is ux and this component is delta u. And kinetic energy is constant. Here the kinetic energy is half m naught u square plus half m naught u square, and here it should be the same kinetic energy, and therefore, the speed of the particle, that should be u here and u here, the same u, so that the kinetic energy half m u square m naught u square plus half m naught u square, here also it should be half m naught u square plus half m naught u square. So, it should be same. So, all these things I am telling from Newtonian mechanics, but even otherwise the kinetic energy will depend on u, even if it is not half m u square, it will depend on u and mass, and since the two particles are having same mass, the two speeds have to be same. Now, this is from our lap frame, say S frame. So, in this frame, linear momentum is conserved and kinetic energy is also same. Before and after collision. Same thing here, linear momentum is same, conserved means same before and after collision. Very nice. Now, look at this whole phenomena from the frame S prime, and S prime will be moving with respect to this S frame in the x direction, positive x direction, with speed, let us say this u. So, I take S prime. So, if this is S, let us take S prime, this is S prime, which is moving with respect to S with a speed u. So, in this S prime frame, what will be the situation? What are the velocities before the collision and after the collision? So, you remember the velocity transformation equations. If you have a particle, suppose this is S, in S you have a particle which is going with some component ux here and ui here, and then you have a frame S prime, and S prime goes with a velocity v with respect to S. Our transformation equations for velocity was that this in S prime frame, from S prime frame, if you look at this particle, then you will have ux prime, which is ux minus v over 1 minus ux v by c square, and then you have ui prime, which is ui, and then square root of 1 minus v square by c square, and then divided by 1 minus ux v by c square. These are the velocity transformation equations, we had derived this. So, using these equations, I can write what will be the velocities, speeds, the components in S prime before the collision and after the collision. But before going that, let me do something else. Since we have taken delta u as a small quantity and quantity, what we will do is whenever it is added to a finite quantity, we will neglect that. So, if I look at the kinetic energy here or speed here, let us take this as speed here. So, for this particle, this is particle B after the collision. What is the speed? The speed is u. So, this u, this is the speed, square is equal to ux square and plus this delta u square. So, ux square is equal to u square and minus delta u square. So, you can see that this is a finite quantity and this is infinitesimal. So, in presence of this I neglect this and hence this is u square and hence I can write ux as u. Okay. So, this ux is u and this ux is u. So, let me write that. Here I have this particle here going in this direction, there is a small y component which is delta u and the x component still remains u and this speed is also u. Okay. It may look very peculiar, but remember delta u is a small first order small quantity as compared to u, and therefore, just like sin theta by theta goes to 1 when you have small theta, similarly this u square plus delta u square will go to u square when this delta u is small as compared to this u. So, we have taken that particular case and therefore, your components are u and delta u here and similarly u and delta u here. So, now let us use transformations to these transformations to get the speeds, to get the components in S prime frame. So, now I am writing from S prime frame. Now, this particular particle is going with a speed u in the lap frame and this frame S prime is also going in the same direction with the same speed. So, this particle will be at rest here. So, our picture is that this particle is at rest, this A particle is at rest. And what happens to B particle? This B particle is coming in this direction, it is coming in this direction and when you use that equation, this equation, remember your ux is now minus u and therefore, it will be the speed will be 2u by 1 plus u square by c square. This ux is minus u and this v is u. So, it is 1 plus u square by c square. So, this is before the collision. After the collision what happens? So, let us start with this. A particle is here, A particle is here, this is let us say A particle, x component. Here this x component is u and the frame S prime is also moving with the same speed u in the same direction. So, this component will be 0, ux prime will be 0, this ux is u and this v is also u, both in positive direction. So, this particle will just go in this direction. So, x component is 0 and what is y component of velocity? This is delta u. So, you have to use this equation here. So, this will be uy, that is delta u, multiplied by square root 1 minus frame velocity v here. So, that is u square by c square, then divided by 1 here minus ux. So, it is minus u frame velocity again u divided by c square, and therefore, this is delta u divided by square root 1 minus u square by c square. So, that is particle A. right? This particle A comes from this side, makes a collision here, deflects, goes this way. So this is A particle, and the x component is u, the y component is delta u, and then we are making transformations, and in the transformation I have ux coming here, and this v coming here. V is the frame velocity, this v is the frame velocity, frame speed, and this ux is the component of velocity in s frame, in s direction, x direction. And therefore when you use this in this frame, this A particle is here, and its x component is u. So for ux you will be writing u. So all this ux here you will be writing u, and that's what we have done. And then v is the frame velocity, which is also u, and therefore it is this. Come to this B particle. This is the B particle. So come to this B particle. What is the velocity in x direction? The particle is going in u with speed u in minus x direction. The frame is going with speed u in plus x direction. And therefore in s prime it will have a speed in this direction, and that will be again 2u by 1 plus u square by c square. And y component is delta u here. So similar transformation, the y component will be here, and that will be what? That will be delta u. Look at here, uy, this is uy, and then square root of 1 minus v, frame velocity, which is u here, so u square by c square, divided by 1 minus ux. Ux is the velocity of the particle in x direction, x component, ux, this ux I am writing, this ux here. It is the velocity of the particle x component in s frame. So here is the velocity in x direction, x component in s frame, and that is minus u. So for this ux I will be writing minus u, and therefore it will be plus here u, and this is frame velocity, which is again u. So it is plus u square by c square. So plus u square by c square. Now you see, if I define the linear momentum as mass times velocity, so the mass here is m naught, the mass here is m naught. In x direction if I see, the momentum here is p is m naught times velocity. Velocity is this 2u by 1 plus u square by c square in negative x direction. That is the linear momentum here. Py is 0. So this is the whole linear momentum. Px is this and py is 0. What about this picture after the collision? In x direction if you see px, so here the px will be, see, p is mass times velocity, so px is mass times x component of velocity, and x component is this, so it is minus m naught 2u by 1 plus u square by c square. Here this is 0, it does not have any x component in the velocity. So this is the total px, and what was total px here? The total px here was minus m naught 2u by 1 plus u square by c square. So yes, the x component of the linear momentum is conserved. Before the collision it is this, after the collision it is this. What about y component? Y component here is 0. Y component here is 0, and y component here is not 0. Look at the velocity here. This is the speed, this is the y component, and this is the y component. So py, if you are writing this not 0, it not come out to be 0, it will be minus m naught times this thing delta u and square root 1 minus u square by c square divided by 1 plus u square by c square. This will be Py here, and from here Py is this, so plus m naught and then this delta u divided by square root of 1 minus u square by t square here. So you can see that this is not 0. Okay, so we have done the velocity transformation according to Lorentz transformation, and what we find is that if we are taking this special example, specific example, mass m naught here, mass m naught here, u here, collision, and then kinetic energy same before and after, that tells me that for the first order of small quantity this will be u, this will be delta u, this will be u, that will be delta u, and from here we have done all these transformation equations, we have written all this px and py before the collision, and then we made the transformation here, and what we are writing is px here and py here, and we find that this is not 0, this was 0. So if we define linear momentum in this fashion, it is not conserved in the two frames, and this linear momentum conservation principle comes from Newton's law, remember. So Newton's law is not being valid here if v is not very small as u is not very small as compared to c. So that is the thing which forces us to redefine linear momentum. If we say that okay, fine, let us redefine this linear momentum in such a way that when v is much smaller than c, it should reduce to this equation. It is a very nice equation, p equal to mv, and then this p remaining conserved if external force is 0 is extremely good principle. We cannot do away with that. So when low velocities, at low velocities, the linear momentum should reduce to this, but then at higher velocities, or in general the linear momentum should have a slightly different expression from this, which should reduce to this when you go to this lower velocities limits. So how to do that? How to redefine this so that linear momentum principle, conservation principle remains valid? That is the thing that we have to take next.